Let's continue the discussion on how to use the permutation and combination approach to count the favorable outcomes and the total outcomes, and how can we do it as an alternate method, how can we do it with the tree diagram. So here is another DSC question. It says that there are 5 white and 11 blue cups if 6 are randomly drawn from the box. Now, if we want to do it with tree diagram, it's going to be complicated, right? Because there are 6 stages. You have to draw 6 times, all right? But anyways, we'll see how we can do it with both methods. But then there's an important hint that all these they are taken at the same time. At the same time, let me remind you again, is without replacement, all right? So the denominator will change. Every time you do the picking, there will be one less item for you to pick from. All right. So we want to, in part A, we want to find the probability that at least 4 white cups are drawn. All right. So in part A, we want to do the probability at least 4 whites. Now, what does at least 4 whites means? At least 4 whites means there is 4 whites, 5 whites, or 6 whites. All right. There are only 6 cups to be drawn. All right. Now, if there is 4 whites, then there is 1 blue. All right. If there are 4 whites, there are 2 blues. 5 whites, 1 blue. 6 whites, no blue. All right. But since we only got 5 whites, so you will never have 6. All right. So this one must be 0. It's never possible. It's impossible to have 6 whites. All right. So 4 whites and 2 blue. Let me invoke the NCR approach. You have 5 whites, you choose 4 of them. So there are 4 ways you can do that. There are 11 blue, and you choose 2 of them. So that is 4 whites and 2 blue. All right. This is on white, and this is on blue. All right. Okay. So the second one will be 5 whites and 1 blue. So 5 whites will be 5C5. 1 blue will be 11C1. Alright. Out of the denominator total, regardless of color, we have 16 clubs, and every time we choose 6 of them. Alright. The denominator is done regardless of color. We have 16 cups altogether, never mind the color. And every time we pick 6 of them. So this is it. Right, we don't have to look at the tree diagram. We don't have to think about how many times the branches they are repeating. We use NCR, NPR to count the favorable outcomes. All right. So 4 whites and 2 blue will be this. So many ways we can do that. 5 whites and 1 blue will be this one. All right. So you have to punch these numbers on the calculator. And the answer goes to 1 out of 28 if you simplify all the fractions. Right? You can do it on the calculator. You can simplify the answers on the calculator. Alright, so this is part A. Alright. Now you may spend some time working on part B. Find the probability that there are at least 3 blue chips. Alright, mind the words. Suddenly it becomes blue. Alright, 3 blue chips. So at least 3 blue. So there are many possibilities now. It can be like 3 blue, and then you have 3 whites. You can have 4 blue and 2 whites. Alright, 3 whites, sorry. And then you can have 5 blue and 1 white. Or you can have 6 blue. There are enough blues, you can do that. There are altogether 11 blue. Alright, so the last one is not a 0. Alright, don't think that, if this is 0, then this is also 0. No, that is not the case, alright? Because there are enough blue cups to take 6 blue. Alright, so this is not always 0, okay? So it's just like that. You just repeat what we did in part A, but this time we do it 1, 2, 3, 4, 4 times. 1, 2, 3, 4. We do it 4 times, alright? Or alternatively, you can think about it in this way, right? Sometimes if you put a little bit thought into it, it can be much faster, alright? At least 3 means that unless there is no blue, alright, 1 blue or 2 blue. Unless there's no blue, 1 blue or 2 blue, then there will be at least 3, right? Unless there is no blue, there is 1 blue, there are 2 blues, alright? So unless is 1 minus. Alright, so that is 1 minus. No blue means no blue, 6 white. And 1 blue means 1 blue, 5 white. Alright, and lastly, that would be 2 blue and 4 white. Alright, so you have to do this calculation again. Alright, so in the first method, you have to do 1, 2, 3, 4 terms. In this 1 minus method, you only do 1, 2, 3, 3 terms. So maybe the second method is easier. Moreover, if you pay attention to it, if you have the insight, suddenly you discover that what is in this orange box is exactly the answer in part A. That is a big revelation. Alright, do you discover? What is in the orange box is exactly the answer in part A. So the simplest way out of this question is just take the answer in part A and 1 minus that answer. 1 minus 1 over 28, and this is it. This is it, right? If you have the insight, noticing that at least 3 blue, that is the exact opposite of at least 4 white. If it is not at least 3 blue, it must be at least 4 white. Alright, so the answer is 1 minus, and that goes to 27 out of 28. Alright. So that's how I did it with the NCR counting approach. Now I challenge you to attempt the same question with a tree diagram approach. Alright, of course you do not have to draw the complete tree diagram. Alright, just think about the corresponding branches. What are some of the interesting branches, alright, that you can consider? Alright, so first you still have to do this analysis that if we want to do it with tree diagram. Alright, if you want at least 4 whites, then it's 4 whites, 2 blue, and 5 white, 1 blue. Alright, 4 white, 2 blue will be the first white is 5 out of 16. The second white will be 4 out of 15, and so on. Alright, so these are how you get 4 whites. And then 2 blue clubs, you are down to 12 clubs. And then 10 over 11. So that is 4 whites and 2 blue. Alright, and this branch is going to repeat 6C2 times. Alright, I leave it to you to figure out how come this number is 6C2. Alright, and then for similar token, we have this. Alright, what I'm doing it now is a tree diagram approach to the same question. I did not draw the tree diagram, right? The tree diagram will be exceedingly complicated. What I'm doing here is try to do the tree diagram without the tree. Alright, I just consider the relevant branches and think about how many times those branches they repeat. Alright, those branches I put them down in red, and the number of repeat is the blue number. Alright. So I'm not mistaken. If you do it on the calculator, I hope you will go back to 1 over 28. Right? Let me try that on my calculator. Okay, so indeed it goes to 1 over 28. Alright, so at least it agrees with the answer from the previous one. Alright. So, well, try to compare these two questions. They're almost the same. Alright, only that the second one is more numerically more complicated. But I did it with NCR, NPR, the counting approach. We count the favorable outcomes, divide by the total outcomes. And then on the bottom of the page, I did it again with the tree diagram approach. Right? I did not draw the tree diagram. It's too complicated. I just think about what are the relevant branches. Alright, and how many times do each relevant branch repeats itself. Alright. Arguably, it is more complicated in the tree diagram approach, but you can choose your favorable method. And then sometimes you don't really have a choice. You have to do it with the NCR, NPR approach, right? So this is a very permutation question. If you have 4 boys and 5 girls randomly forming a queue, right? Find the probability that no boys are next to each other in the queue. So it's not about with or without replacement. It is basically a permutation question. Alright, and that no boys are next to each other, once again, is a very permutation thing. Alright, when we learn about permutation, we learn about two special cases that things must be separated, things must be together. So in other words, this orange box means that the boys must be separated. Right, so it is a very permutation idea. I think it is very complicated to do it with the tree diagram. It's almost impossible. Well, it's possible, but it takes an insane amount of time. But the permutation approach is very simple, right? As long as you know how to do must be separated, right? So first of all, we line up the 4 boys, right? In case you cannot remember it now, that's how we did must be separated. We line up the 4 boys, so that is 4 ways we can do that. Right? Now between the boys, inclusive of the first and the last one, there are 5 positions. Oh, I'm sorry. I should have lined up the girls first. Sorry. I made a mistake. It should be the 5 girls. We line up the 5 girls like this, alright? So to line up the 5 girls, we have 5 ways. Now between the girls, inclusive of the beginning and the end, there are 6 positions. 1, 2, 3, 4, 5, 6. We put the 4 boys into these 6 positions. To do that, we have 6 ways. We can do that. Alright. If we did that, we can guarantee that no boys are together. The boys must be separated. Right? Remember, that's how we do it with must be separated. So that is 5p5, the number of ways to line up the girls. 6p4, the number of ways to put the boys in between the girls. Out of a total, what is the total? The denominator. The denominator will be 9 persons lined up, regardless of gender, regardless of whether they are boy or girl. Alright. Totally, there will be 9p9. 9 persons lines up, 5 plus 4, 9 persons. Alright. So there are so many ways to do that. So this is it. Alright. This is it. 5p5 times 6p4 divided by 9p9. Alright. If you do it on the calculator, the answer is 5/42. Alright. This is it. That would be much easier if you do it with the NPR NCR approach. Alright. Now imagine if you want to do it with tree diagram. Now I can't imagine how I'm going to do it in a tree diagram. It's going to be very complicated. Alright, because there are 9 people to line up. And every time you have a boy branch, you have a girl branch. This is going to repeat 9 times. 2 to the 9th power, at the end you have 512 different events. It's a total nightmare if you are going to do this with tree diagram. Alright. So you have to master both approaches, how to do it with the NPR NCR approach, and how to do it with the tree diagram approach. There are merits in both methods. Alright. So this is it for the probability, and I show you a lot of different DSC questions to illustrate my point. So this is it. Thank you.